Welcome to Still Science Lab. Tonight, we explore a question that sits quietly beneath the surface of modern physics. What if quantum physics is revealing that reality is not built the way we imagined? Not a universe made simply of tiny objects moving through empty space. Not a world where matter has fixed properties waiting patiently to be measured, but something stranger, deeper, and more difficult to picture. A reality shaped by fields, probabilities, relationships, and information. Some of the most sensitive experiments on Earth are designed not to make noise, but to escape it. In laboratories cooled to temperatures near absolute zero, matter is forced into silence. Thermal motion slows. Electrical disturbance is reduced. Devices are shielded from vibration, radiation, and the constant interference of the outside world. The goal is not drama. The goal is stillness. Because somewhere inside that stillness, physicists are listening for signals so faint they would disappear inside ordinary reality. A tiny shift in energy, a click inside a detector, a particle track that appears and vanishes, a correlation that should not exist classically, a pattern repeated across thousands, millions, or billions of events. None of these signals would mean much to the human senses. They are not things we can hold, smell, hear, or see directly. They arrive as data, as traces, as disturbances in instruments built to notice what ordinary perception cannot. But for physics, these small signals can become enormous. They can challenge the way we think about matter, space, time, and what it means for something to be real. This is where quantum physics becomes unsettling. Not because it is fantasy, not because it allows anything to happen, but because it works. Quantum physics is one of the most successful scientific frameworks ever created. It predicts the behavior of atoms, particles, light, materials, and fields with extraordinary precision. It lies beneath the technology of the modern world, from semiconductors and lasers to atomic clocks and advanced sensors. It is not a vague philosophical idea. It is tested, mathematical, and deeply practical. And yet, when we ask what it means, the ground becomes less certain. The deeper scientists look, the less reality resembles the world our instincts were built to understand. At human scales, the world feels solid. Objects have positions. Events have causes. A thing is here, not there. A door is open or closed. A signal travels from one place to another. A measurement reveals a property that was already present. This is the world of common sense, and common sense is useful. It helps us move through rooms, build tools, navigate landscapes, and survive. But common sense is not the foundation of the universe. It is a survival interface. It was shaped by everyday matter, everyday speeds, and everyday distances. It was never designed to understand electrons, photons, quantum fields, entanglement, or measurement. So when the quantum world refuses to behave like the ordinary world, the mistake may not be in nature. The mistake may be in expecting nature to be intuitive. A particle, for example, is not simply a tiny ball. An electron is not a miniature planet orbiting an atomic nucleus in the way a moon orbits a world. A photon is not a little bead of light flying through darkness. These images help for a moment, but they break quickly. In quantum physics, what we call particles are better understood through states and fields. They can appear as localized events when measured, but before measurement, their behavior may be described by waves of probability, by possibilities that interfere, and by mathematical structures that do not fit easily into ordinary language. This does not make them unreal. It makes them quantum. A particle can behave like a wave, spreading its possible outcomes across an experiment. A wave can arrive as a single detected event. Possibilities can interfere with one another, reinforcing some outcomes and cancelling others. Measurement can turn a range of possible results into one recorded fact. two systems can become entangled so that the full information about them belongs not to either one alone, but to the relationship between them. This is not magic. It is stranger than magic, because it is measurable. Magic asks for belief. Quantum physics asks for experiments. It gives predictions, and those predictions can be checked. Again and again, nature answers in a way that violates classical expectation while obeying quantum rules with astonishing precision. That is what something deeply strange really means. It does not mean the universe has irrational. It means the universe may be rational in a way that does not resemble human intuition. It means a result, behavior, or principle has appeared that challenges the classical picture. The idea that matter is made of solid little objects, that space is an empty stage, that information always belongs to individual things, and that measurement simply reveals what was already definite. Quantum physics suggests that the deeper story is more subtle. Matter may be excitation, space may not be empty, information may live in relationships, possibility may have physical structure, and reality at its foundation may not be a list of finished facts waiting to be uncovered. It may be a process by which possibilities become facts through interaction. This is why laboratories searching for quantum signals often feel like places built around restraint. The machines are powerful, but the atmosphere is quiet. Physicists are not expecting nature to announce itself loudly. They are looking for small deviations from ordinary expectation. A detector listens for a particle that barely interacts. A quantum computer tries to preserve fragile states before the environment destroys them. A precision experiment measures whether a particle behaves exactly as theory predicts, or whether a tiny anomaly points towards something deeper. Sometimes the signal disappears. Sometimes the data was incomplete. Sometimes the strange result turns out to be noise, background, or an experimental artifact. But sometimes a strange pattern survives, and when it survives, the meaning can be profound. Because quantum physics is not only about the small, it reaches outward. The behavior of particles influences chemistry, stars, and the early universe. Quantum fields may have shaped the first moments after the Big Bang. Entanglement may be connected to the structure of space-time. Black holes force physicists to ask whether information can ever be destroyed. The smallest rules may be tied to the largest mysteries. This is the emotional scale hidden inside quantum science. A tiny signal in a laboratory may connect to the architecture of reality. A particle measured in a detector may reveal something about fields that fill the universe. A question about measurement may touch the nature of time, causality, and information. A qubit protected in silence may become a clue to how the universe stores possibility. At first, this seems far removed from ordinary life. But ordinary life is built on the quantum world. Every atom in the body, every chemical bond, every photon entering the eye, every electrical signal in a device depends on quantum rules. The strange does not live far away. It is beneath everything familiar. The familiar world is what quantum reality becomes when countless interactions blur its sharpest mysteries into stable experience. The table feels solid because quantum fields and forces produce resistance. The sun shines because quantum processes allow nuclear reactions to unfold. Your thoughts depend on matter whose stability comes from quantum laws. Reality feels classical because we are large, warm, and constantly entangled with our environment. But beneath that surface, the deeper rules remain. And those rules are telling us that the universe is not built like a machine of tiny hard parts. It is more like a layered structure of fields, states, probabilities, and correlations. The objects we know may be emergent patterns. The properties we measure may not always exist in the same way before measurement. The distance between things may not fully describe their quantum relationship. The information in a system may not belong only to its parts, but to the whole. This does not make reality less real. It makes reality deeper than the map our senses gave us. That may be the most important shift. Quantum physics is not asking us to abandon reality. It is asking us to abandon a simplistic version of it. The universe is not unreal because it is strange. It is strange because our instincts evolved in a narrow region of its behavior. We learned to understand falling objects, flowing water, burning fire, and solid ground. But the foundation beneath those things was always stranger than survival required us to know. Science is the act of going beyond what survival taught us. It builds instruments where senses fail. It builds mathematics where language fails. It builds experiments where imagination fails. And in the quietest places on Earth, in cold laboratories and shielded detectors, scientists continue to ask whether the strange signal beneath reality is telling us something new. Maybe matter is not what we thought it was. Maybe space is not as empty as it seems. Maybe information is not secondary, but fundamental. Maybe measurement is not just observation, but a physical threshold where possibility becomes record. These are not final answers. They are openings. And that is where the mystery becomes powerful. Quantum physics has not made the universe less knowable. It has made knowledge more careful. It has shown that reality can be precise without being intuitive, structured without being simple, and deeply lawful without one matching the expectations of human common sense. The deeper scientists look, the less the universe behaves like ordinary objects moving through empty space. Instead, it behaves like something quieter and stranger. A web of fields, a grammar of probabilities, a structure of relationships, a hidden order beneath the visible world. And somewhere inside that order, the next great discovery may already be waiting. Not as a shout, but as a signal almost too subtle to hear. Quantum physics feels unfinished not because it fails, but because it succeeds in a way that leaves us uneasy. It is one of the most accurate scientific theories ever created. Again and again, it has predicted the behavior of matter, light, atoms, particles, and fields with astonishing precision. It explains why atoms are stable, why chemistry works, why materials conduct or insulate, why lasers can exist, why semiconductors power modern electronics, and why the microscopic world behaves with the patterns we measure in laboratories. It is not a weak theory. It is not a temporary patch. It is one of the great pillars of modern science, and yet beneath its success, there is a strange discomfort. Quantum physics tells us how to calculate what will be observed. It tells us what probabilities to expect, what patterns will appear, what measurements will reveal, and how systems evolve when left undisturbed. It gives us a mathematical machine of extraordinary power. But when we ask what the mathematics means, the clarity begins to dim. What is a particle before it is measured? What is a wave of probability? Does a quantum state describe reality itself, or only our knowledge of reality? When measurement produces one result, what happens to the other possibilities? Why do entangled particles behave as though their relationship matters more than ordinary distance? These are not small questions. They sit at the philosophical center of quantum theory, and more than a century after the theory first transformed physics, they remain difficult. That is the reason quantum physics feels unfinished. It works almost too well to ignore, but it speaks in a language our intuition was never built to understand. In the ordinary world, things appear definite. A stone lies in one place. A planet follows a path. A light is on or off. A measurement reveals a property that seems to have been there before we checked. We live in a world where objects seem separate, stable, and located. Our minds evolved inside that world, so it feels natural to assume Reality must be built that way, all the way down. Quantum physics tells us that assumption is wrong. At the smallest scales, particles do not behave like tiny solid objects. An electron can produce interference patterns as if its possible paths behave like waves. A photon can be detected as a single event, yet its behavior before detection may require a wave-like description. Matter and light refuse to stay inside the categories we prefer. They are not simply particles or waves in the everyday sense. They are quantum systems, and our familiar words are only imperfect approximations. This is deeply unsettling, because it means the basic building blocks of reality are not miniature versions of the things we already know. A particle is not just a tiny pebble. A wave is not just water moving across a surface. A quantum object is something stranger, a physical system whose state can encode possibilities, correlations, and probabilities before a definite result appears. And then comes measurement. In classical physics, measurement feels passive. To measure something is to discover what was already true. If you weigh an object, you assume it already had that weight. If you check a switch, it was already on or off. The act of observation may disturb some delicate systems, but in principle, the property existed before you looked. Quantum measurement does not fit that simple picture. Before measurement, a quantum system can be described by multiple possible outcomes. After measurement, one outcome is recorded. A detector clicks. A number appears. A trace is left. The system that once required a quantum description now produces a classical fact. But what exactly happened? Did the measurement reveal a hidden answer that was there all along? Or did the interaction help create the outcome? Quantum physics gives reliable probabilities for the result. But the meaning of the transition remains one of the deepest unresolved issues in the foundations of the theory. This does not mean consciousness magically creates reality. That is our common overstatement. In physics, measurement means a physical interaction that produces a stable record. A particle hits a detector. A photon is absorbed. A system becomes entangled with its environment. The result becomes part of the world in a way that can be copied, shared, and remembered. But even with that careful definition, the mystery remains. Before measurement, quantum information is structured possibility. After measurement, it is recorded fact. Somewhere between those two descriptions, the world we experience emerges. That boundary is why quantum physics feels complete in calculation, but incomplete in interpretation. Entanglement makes the discomfort even deeper. When two particles are entangled, the full information about the pair cannot be separated into independent descriptions of each particle alone. The relationship between them becomes part of the quantum state. Even if the particles are far apart, their measurement results can show correlations stronger than anything classical physics allows. This does not allow faster-than-light communication. No usable message can be sent instantly across space. Relativity survives, but the classical idea of separateness does not survive unchanged. Entanglement suggests that nature does not always build the whole from independent parts in the way we expect. Sometimes, the whole carries information that the parts do not possess separately. The relationship is not just a secondary detail. It is part of the physical description. That idea is quiet but radical. It means distance may not be the only measure of connection. It means two systems can be far apart in space, yet still belong to one quantum description. It means information can live in correlation, not only in objects. For a theory that works so well, quantum mechanics gives us a reality that feels almost incomplete from the inside. It tells us what will happen statistically, but it does not satisfy the older desire for a simple picture. It replaces her certainty with probability. It replaces isolated objects with states and relationships. It replaces passive measurement with physical interaction. It replaces the comfort of common sense with a deeper order that is precise but strange. And that precision is what makes the mystery harder to dismiss. If quantum physics were vague, its strangeness would not matter as much. But it is not vague. It is tested. It is engineered. It is built into devices. It is used every day. The modern world runs on quantum principles, even if the meaning of those principles remains debated. This is the unique tension. Quantum physics is practically complete enough to build technology, but philosophically open enough to disturb our idea of reality. It can tell us how an atom emits light. It can tell us how electrons behave in a material. It can guide the design of a quantum sensor. It can predict the outcome of experiments with extraordinary accuracy, but it still leaves us asking what a quantum state really is. A tool for prediction, a physical entity, a description of knowledge, a description of possibility, a deeper layer of reality. Different interpretations offer different answers. Some suggest that the wave function represents reality itself. Others suggest that it represents information available to an observer. Some propose that all possible outcomes occur in a broader branching structure. Others modify the theory so that collapse becomes a physical process. Still others look for deeper hidden variables, though experiments have placed severe limits on how such ideas can work. The debate continues because the experiments tell us what nature does, but not always how to picture what nature is. This is not a failure. It is a sign that science has reached a level where old concepts are no longer enough. Every major revolution in physics has done this. Newton gave us a universe of forces and motion. Maxwell revealed fields and light. Einstein changed space and time. Quantum theory changed matter, measurement, and possibility. Each step did not simply add new facts. It changed the meaning of familiar words. Object, location, cause, state, reality. Quantum physics forces all of them to become more careful. Perhaps this is why it continues to feel unfinished. Not because the equations are weak, but because the human mind still wants a story that feels like the world it knows. We want particles to be little things. We want properties to exist before measurement. We want distance to separate systems cleanly. We want probability to mean ignorance, not something built into the structure of events. Quantum physics refuses to give us that comfort. It gives us something better but harder. A theory that matches nature more closely than intuition does. A map that works even when the landscape feels impossible. And perhaps the unfinished feeling is not only in the theory, perhaps it is in us. Our instincts were shaped by a classical world that emerges from quantum rules but hides their strangeness. We are trying to understand the foundation of reality, with minds evolved to navigate its surface. That does not make understanding impossible. It makes it profound. Quantum physics works incredibly well. It is one of the clearest successes of human reason, but what it says about reality is still deeply unsettling. It suggests that the world beneath appearances is not made of definite little objects alone, but of states, possibilities, fields, measurements, and relationships that become definite only through interaction. The theory is finished enough to be true in every experiment we can test, but unfinished enough to keep asking what truth means, and somewhere inside that tension, between calculation and meaning, between prediction and reality, quantum physics remains one of the strangest mirrors the universe has ever held up to the human mind. The word particle is one of the most useful words in physics, and also one of the most misleading. It makes us imagine something small, solid, and separate. A tiny dot moving through space, a miniature grain of matter, a little object with a surface, a path, and a definite location, like a planet reduced beyond visibility. This picture feels natural because it borrows from the world we know. Rocks, dust, droplets, planets, and machines all seem to be made of pieces. If matter is made of smaller things, then perhaps those smaller things are just smaller versions of objects. But the quantum world does not work that way. An electron is not a tiny ball. A photon is not a little bead of light. A quark is not a microscopic pebble trapped inside a proton. These images can help at first, but if we hold onto them too tightly, they hide the deeper truth. What physics calls a particle is not necessarily a tiny solid object moving through empty space. In modern physics, particles are better understood as excitations of underlying quantum fields. That sentence sounds abstract, but it is one of the most important ideas in our picture of reality. A field is something that exists across space. The electromagnetic field is associated with light and electric and magnetic effects. The electron field is associated with electrons. Other fields are associated with other particles. In quantum field theory, what we call a particle is a localized excitation of a field, a small packet of activity in something more fundamental and more spread out than an ordinary object. A particle is not a thing sitting on top of reality. It is a way a field can become active. The familiar world makes this difficult to imagine because ordinary experience is built from surfaces. We touch the table and feel resistance. We pick up a stone and feel weight. We see objects with edges and locations. The world seems made of solid pieces because that is how it behaves at human scales. But solidity is not the same as fundamental simplicity. What feels solid is the result of quantum fields, forces, and exclusion principles organizing matter into stable structures. Matter is real, but it is not real in the simple way our senses suggest. When an electron is measured, it can produce a localized event. A detector may record a click. A screen may show a dot. An instrument may register energy at a particular place. This makes the electron feel particle-like because the final record is specific. Something happened here, not everywhere. But before measurement, the electron's behavior may not be described as a tiny object following one definite path. Its quantum state can be spread across possibilities. It may pass through an experiment in a way that produces interference, as if different possible paths matter at the same time. The final measurement gives one result, but the pattern built from many such events reveals a wave-like structure underneath. This is the strange balance. Particles appear as local events when they interact, but their behavior before interaction can be extended, probabilistic, and wave-like. This is not because the particle is confused. It is because particle and wave are both classical words, trying to describe something that is not fully classical. Quantum objects do not fit cleanly into either category. They can act like particles in one situation and like waves in another, not because they switch costumes, but because our categories are incomplete. A photon can arrive as a single detection event, but its probability can spread and interfere before that event. An electron can strike a detector at a point, but its state may evolve like a wave of possibility before measurement. Matter is not simply made of little solid things. It is made of quantum states governed by fields. This is the gentle fracture in intuition. We want the smallest ingredients of matter to be understandable as smaller versions of the things they create. But nature does not owe us that symmetry. A wave in the ocean is not a tiny version of a coastline. A sound is not a tiny version of a musical instrument. Temperature is not a tiny hot particle hidden inside matter. Large-scale experiences can emerge from deeper rules that do not resemble them. The same is true of particles. The world of chairs, bodies, mountains, and stars emerges from quantum rules, but those rules do not look like the objects they produce. At the deepest level we can test, reality is not a pile of miniature solids. It is a network of fields and states. Fields fill space. Their excitations behave as particles. Their interactions produce forces, radiation, decays, and structure. Quantum states describe the possible outcomes of measurement. Probabilities are not just tools for human ignorance, they are built into how the theory connects the hidden state to observable events. This changes what it means to ask where a particle is. In the classical world, location seems straightforward. A ball is somewhere, a planet is somewhere. Even if we do not know where it is, we assume it has a definite position. But in quantum mechanics, a particle may not have a definite position in the same way before measurement. Its state may assign probabilities to different possible locations. When measured, one outcome appears. But the prior state was not simply a small object hiding at one point. This is why the famous image of electrons orbiting the nucleus, like planets around a star, is misleading. Atoms are not tiny solar systems. Electrons in atoms occupy quantum states. These states are often described as orbitals, but orbitals are not paths. They are patterns of probability, regions where an electron is likely to be found if measured. The electron does not circle the nucleus like a little moon. Its behavior is defined by a quantum state shaped by the electromagnetic interaction and the rules of quantum mechanics. The result is stable matter, chemistry, structure, the world. But the foundation is not a mechanical clockwork of tiny balls. It is a mathematical and physical structure of fields, states, and interactions. Photons deepen the mystery. Light behaves as a wave in many situations. It bends, interferes, diffracts, and spreads. Yet, when light is detected, it often appears in discrete events as if energy arrives in packets. A single photon can build an interference pattern over many repetitions, even when photons are sent one at a time. The pattern reveals wave-like behavior. The detection reveals particle-like discreteness. Neither picture alone is enough. The photon is not just a little bullet of light, and it is not just a classical wave. It is a quantum excitation of the electromagnetic field. The same kind of idea extends across modern particle physics. Every known particle is associated with a field. Electrons, quarks, neutrinos, photons, gluons, and other particles are not isolated objects added into empty space. They are field excitations, manifestations of underlying quantum structures. Empty space itself is not simply nothing. It is the lowest energy state of fields, capable of fluctuations and interactions under the right conditions. This view is less intuitive, but more powerful. It explains why particles of the same type are truly identical. Every electron in the universe is an excitation of the same electron field. One electron is not manufactured with slightly different material from another. It is the same kind of quantum event arising from the same underlying field. This is why electrons behave identically everywhere we observe them, whether in a laboratory, inside a star, or in a distant galaxy. The universe has consistency because its fields are universal. A particle is local, but the field is everywhere. That is a profound reversal of the old picture. Instead of imagining the universe as empty space filled with little objects, modern physics imagines fields as primary, with particles appearing as quantized excitations of those fields. The object-like world emerges from field behavior. The solid world emerges from quantum structure. This does not make particles fake. A particle detection is real. A photon absorbed by a sensor is real. An electron scattering from another particle is real. A proton inside an atomic nucleus is real. But the reality is not the simple reality of tiny, hard spheres. It is the reality of quantum fields producing measurable events. The word particle survives because it is useful. It points to discrete interactions, countable excitations, localized detections, and measurable properties like charge, spin, and mass. But it should not trap the imagination inside a classical picture. A particle is not a miniature object in the ordinary sense. It is the way a quantum field shows up when the universe is asked a question through interaction. This matters because our picture of matter shapes our picture of reality. If matter were made of tiny solid things, then the universe might be imagined as a machine built from little parts. But if matter is made of quantum fields and states, then reality is less like a machine of objects and more like a structured pattern of possibilities becoming events. The world is not less real, it is more subtle. The table is still there, the body is still real, the stars still burn, but beneath their apparent solidity is something different from everyday intuition. Fields fill space, quantum states or evolve, interactions create records, measurement produces definite outcomes. The familiar world appears when countless quantum processes become stable enough to behave classically. This is why particles are not tiny objects. They are not small versions of stones. They are not little planets. They are not beads moving through a void. They are excitations, events, states, and relationships in quantum fields. They can appear at a point when measured, but before your measurement, their behavior may be spread across possibility. They can behave like waves, interact like particles, and belong to fields that extend across the universe. Matter, at its foundation, is not built from little solid things in the way we imagine. It is built from quantum states and fields. And perhaps this is the first truly strange lesson quantum physics gives us. The world becomes solid only after its deeper reality has already done something far more mysterious. Probability is usually the language we use when knowledge is missing. A storm may arrive tomorrow, but we do not know how the atmosphere will evolve in every detail. A coin may land heads, but we do not know the exact motion of the hand, the spin, the air resistance, or the surface it will strike. A shuffled deck has a top card, but until someone turns it over, we speak in chances. The uncertainty belongs to us. The world, we assume, has already made up its mind. That is classical probability. It is a measure of incomplete knowledge. Something has happened, or something is already determined by details we do not fully know. Probability becomes a practical tool, a way to navigate complexity. It does not usually mean reality itself is undecided. It means the observer lacks information. Quantum probability is different. At the quantum level, probability appears to be woven into the structure of the theory itself. A quantum state does not always describe a definite object with hidden properties waiting quietly to be revealed. Instead, it describes a set of possible outcomes and how likely each outcome is when a measurement is performed. The uncertainty is not merely a sign that we are missing a few ordinary details. It seems to be part of how nature connects the quantum state to observable reality. This is one of the most unsettling ideas in all of physics. Quantum physics does not always tell us what will happen once. It tells us the pattern realities it will follow over many events. A single particle may arrive at one location on a detector, but if the experiment is repeated again and again with the same preparation, a pattern slowly appears. At first, there may be only scattered points. Then, a structure emerges. The individual event may be unpredictable, but the distribution is not. The randomness is not lawless. It follows a precise order. This is the strange discipline of quantum probability. The theory may not say exactly where one particle will be found in a single measurement, but it can predict the overall pattern with astonishing accuracy. It tells us which outcomes are possible, which are impossible, and which are more or less likely. It does not give certainty for every individual event. It gives structure to uncertainty. That distinction matters, because quantum probability is not the same as chaos. It is not the universe shrugging. It is not a failure of science. It is a different kind of law. In classical physics, if we knew every detail of a system perfectly, we might imagine predicting its future exactly. The coin toss would no longer be random. The weather would be calculable, at least in principle. The path of a planet could be traced forward. The uncertainty would come from limited knowledge, limited measurement, and the practical difficulty of tracking enormous complexity. Quantum physics changes the meaning of in principle. Even when a quantum system is prepared in the same way, even when the experiment is controlled with extreme precision, the theory may only provide probabilities for individual outcomes. Two identical preparations can lead to different measurement results. Not because the equipment is sloppy, not because the particle is mischievous, but because the quantum state itself does not always correspond to one definite classical outcome before measurement. This is where intuition begins to fail. We want probability to be ignorance. Quantum theory suggests it may be deeper. A quantum state is a compact description of possibility. It contains information about what a system can do, how it can respond, and what results may appear when it interacts with a measuring device. But it is not just a list of ordinary chances. It includes amplitudes, and amplitudes can interfere. Some possibilities can reinforce one another, others can cancel. This interference is why quantum experiments produce patterns that ordinary probability alone cannot explain. The famous interference behavior of particles is not just a curiosity. It is a sign that quantum possibilities have structure before measurement. If particles were merely tiny objects following hidden classical paths, we would expect one kind of pattern, but experiments show another. Even when particles are sent one at a time, the accumulated results can reveal interference. The final detections are individual events, but the pattern is shaped by the quantum state. One event is uncertain. Many events reveal order. This is a new kind of predictability, not the predictability of a clock, where each gear determines the next motion exactly. Not the predictability of a thrown stone, where a path can be calculated if enough details are known. Quantum predictability is statistical. It lives in repetition. It says, prepare the same state many times, measure it the same way, and reality will produce a pattern. That pattern is not optional. It is not approximate in some casual sense. It is one of the most precise things science has ever measured. This is why quantum probability feels both humble and powerful. Humble, because it does not give us total certainty about individual events. Powerful, because it predicts the structure of uncertainty with extraordinary success. There is a quiet philosophical shock in that. The universe may not be fundamentally committed to giving every event a definite hidden answers before it is measured, at least not in any simple classical way. Instead, it may carry a quantum state that encodes possibilities. Measurement does not merely uncover a known value in the old sense. It produces a definite outcome from a structure of potential results. This does not mean anything can happen. Quantum outcomes are constrained. A particle cannot simply appear with any energy, any charge, or any behavior we imagine. The quantum state and the laws governing it define the possible results. Probability is not freedom from law. It is law expressed differently. The quantum world is not unpredictable because it has no order. It is unpredictable in single events because its orders is not classical determinism. The order lives in the pattern. That pattern can be seen everywhere quantum physics operates. In the energy levels of atoms, in the decay of unstable particles, in the absorption and emission of light, in the behavior of electrons inside materials, in the way photons arrive at detectors, in the statistics of particles created in high-energy collisions. Again and again, nature refuses to promise one exact event, but delivers the predicted distribution across many events. This is why quantum mechanics can power technology while still disturbing philosophy. A laser works because quantum transitions follow rules. Semiconductors work because electrons in materials obey quantum statistics. Atomic clocks work because atoms have precisely defined quantum energy transitions. Medical imaging, sensors, electronics, and communication technologies all depend on quantum behavior being reliable. But reliable does not always mean deterministic in the classical sense. The reliabilities is in the probabilities. The same idea appears in radioactive decay. An unstable atom has a probability of decaying over a certain time. For one individual atom, quantum theory may not tell us exactly when the decay will happen. But for a large collection of identical atoms, the pattern becomes predictable. The half-life of the material emerges with remarkable consistency. One atom is uncertain. Many atoms obey a law. This is not ignorance in the ordinary sense. There is no hidden ticking clock inside each atom that we can simply read more carefully, at least not in the standard interpretation. The decay is governed by quantum probability. Reality gives us a predictable pattern without giving us a predictable individual event. That can feel incomplete, but it may only feel incomplete because our minds expect certainty at the wrong level. Human beings are used to stories: one cause, one effect, one object, one path, one event, one reason. Quantum physics gives us something more abstract: a state, an interaction, a probability, and a recorded outcome. It replaces the old desire for a hidden classical narrative with a measurable structure that works. And perhaps that is what makes it so strange. Quantum physics does not fail to describe reality. It describes reality in a way that refuses to become a simple story. The role of probability also changes the meaning of knowledge. In the classical world, knowing more means reducing uncertainty. If we gather enough information, the probabilities narrow. With perfect knowledge, at least in principle, uncertainty could disappear. But in quantum physics, some uncertainty seems irreducible. A quantum state may be completely known and still only predict probabilities for certain measurements. Complete knowledge does not always mean certainty. That sentence is one of the quiet revolutions of modern physics. It means the limit may not be in the observer alone. It may be in the structure of what can be known. The quantum state can be fully specified, yet the measurement outcome may remain probabilistic. Nature may allow precise predictions of patterns while withholding certainty about individual events. This has led to many interpretations, and physicists still debate what the probability means at the deepest level. Some interpretations treat it as fundamental randomness. Others suggest that all possible outcomes occur in a broader structure. Others seek deeper hidden variables, though experiments strongly constrain how such hidden variables could behave. The debate remains open because the mathematics works, but the meaning is difficult. Still, the experimental fact remains. Quantum probability is not ordinary ignorance. It is built into the way the theory connects possible states to actual measurements. And when we accept that, the world begins to look different. Reality is no longer simply a collection of definite facts unfolding like a mechanical script. At the quantum level, it becomes a structure of possibilities governed by laws, producing definite events through interaction. The future is not arbitrary, but it is not always pre-written in the classical sense. The universe becomes less like a machine of fixed answers and more like a precise generator of outcomes, not random noise, not mystical uncertainty, but lawful probability. This is why the role of probability in quantum physics matters so deeply. It tells us that nature's deepest rules may not be about predicting every single event with certainty. They may be about predicting the shape of possibility itself. They may define the patterns by which reality produces facts. A single measurement gives an outcome. Many measurements reveal the law. One particle may seem unpredictable, The pattern of particles reveals order, and somewhere in that difference lies one of the deepest lessons quantum physics has given us. Reality may not always tell us exactly what will happen once, but it tells us, with extraordinary precision, the pattern it will follow when the question is asked again and again. That is not weakness. That is the strange strength of the quantum world. A universe where uncertainty is not the absence of law, but one of the ways law appears. Entanglement is where quantum physics becomes impossible to translate cleanly into everyday language. Not because it is vague, not because it is mystical, but because it reveals a kind of connection that the classical world never prepared us to expect. In ordinary experience, distance seems to separate things. A stone in one place has its own properties. A lamp in another place has its own state. A planet, a person, a particle of dust. Each object appears to carry its own information. If two things are far apart, we assume they are independent unless something travels between them. A signal, a force, a message, a physical influence moving through space. This is the world our intuition understands. Objects exist. Space separates them. Signals connect them. Quantum entanglement does not fit comfortably inside that picture. When two particles become entangled, the full information about the system cannot be separated into two complete, independent descriptions. It is not enough to say, here is particle 1 with its own private state, and there is particle 2 with its own private state. The relationship between them becomes part of the quantum state itself. The information belongs to the pair, not just to the pieces. This is a subtle idea, but it changes everything. Imagine two particles created together in a shared quantum process. They move apart. One travels in one direction, the other travels in another. In ordinary thinking, once they are separated, each should carry its own properties with it. Even if we do not know those properties yet, we imagine they are already there, waiting to be revealed. Quantum mechanics says the situation can be different. The pair can be described by one shared state. The individual particles may not each possess a complete set of definite properties in the classical sense. Instead, what is definite is the relationship between possible measurement outcomes. If one particle is measured, the result will be correlated with the result of measuring the other. And those correlations can be stronger than anything allowed by classical physics. This is why entanglement disturbed Einstein so deeply. He believed that physical reality should be local, that distant objects should not be able to affect one another instantly, and that particles should carry their own definite properties, independent of measurement. Entanglement seemed to challenge that worldview. It suggested that quantum mechanics was either incomplete or that nature was far stranger than the classical picture allowed. Decades of experiments have made the conclusion difficult to avoid. Nature really does produce entangled correlations. They are not just a failure of imagination. They are not merely hidden instructions written into the particles from the beginning, at least not in any ordinary local classical way. Experiments testing Bell's inequalities have shown that entangled systems violate the limits that classical hidden variable theories would obey. The results match quantum mechanics. Again and again, the universe chooses the stranger answer. But here, care is essential. Entanglement does not allow faster than light communication. It does not let anyone send a message instantly across the universe. It does not allow a person measuring one particle to control what message appears at the other end. If two observers are far apart, and each measures one particle from an entangled pair, each observer sees an outcome that appears locally random. There is no usable signal hidden in that randomness. Only later, when the observers compare their results through ordinary communication, do the correlations become clear. That comparison cannot happen faster than light. So relativity is not broken. No controllable message outruns light. No cosmic telephone is created. And yet, something deeply non-classical remains. The particles behave as parts of a single quantum system, even when separated. The full information is not stored independently in each object. It exists in the structure connecting them. The relationship has become physically meaningful. This is the heart of entanglement. In the quantum world, information can belong to the connection, not just the objects. That sentence sounds almost philosophical, but it is also experimental. Entanglement is measured, tested, and used. It is not an abstract speculation. It is the basis for quantum communication, quantum cryptography, quantum teleportation of states, and the power of many quantum computing systems. Laboratories can prepare entangled photons, ions, atoms, and superconducting circuits. Scientists can measure the correlations and verify that they exceed classical expectations. The mystery is not whether entanglement exists. The mystery is what it tells us about reality. In the classical world, the whole is usually built from the parts. If we know everything about each part separately, then we know everything about the whole. A machine can be disassembled into components. A message can be broken into bits. A system can be analyzed by studying its pieces. Quantum entanglement breaks that simple assumption. The whole can contain information that is not present in the parts alone. Two entangled particles can each appear individually uncertain. Measured separately, each may give results that look random. But measured together and compared, a pattern emerges. The randomness is not independent. It is coordinated in a way that only the shared quantum state can explain. The information is not here. It is not there. It is in the relation. That is profoundly different from ordinary separability, and it forces us to rethink what an object really is. Perhaps at the deepest level, an object is not only a thing with properties, perhaps it is also a node in a structure of relationships. Its meaning may depend not only on what it is by itself, but on how it is correlated with other systems. This does not mean everything is instantly connected in a mystical sense. Quantum entanglement is specific. It must be created or preserved under physical conditions. It is fragile. Interactions with the environment can destroy its useful form. Large objects around us do not usually display obvious entanglement effects because they are constantly interacting with air, light, heat, and countless surrounding particles. Their quantum information becomes spread into the environment, making the world appear classical, definite, and separate. But at the foundational level, entanglement is not an exception. It is one of the natural languages of quantum mechanics. When systems interact, they often become entangled. When they become entangled with their environment, classical reality begins to emerge. In this sense, entanglement is not just a strange trick. It may be part of how the ordinary world gets built from quantum rules. The definite world may arise because quantum information becomes distributed too widely to track. That is a quiet and powerful idea. The separateness we experience may not be fundamental. It may be the result of quantum relationships becoming hidden in complexity. The world looks classical, not because quantum world is superpairs, but because its delicate correlations are scattered into the environment. Entanglement also reaches into some of the deepest questions in modern physics. Some approaches to quantum gravity suggest that space-time itself may be connected to patterns of entanglement. This is not settled science, and it must be treated carefully. But the possibility is extraordinary. It suggests that the geometry of space, the idea that one region is near another or far from another, may not be the deepest structure. Perhaps geometry emerges from a more fundamental network of quantum information. If that is true, then entanglement is not only strange behavior inside space, it may be part of what makes space meaningful. Again, this is frontier physics, not a final conclusion, but black holes, quantum information, and entanglement have already forced physicists to take the idea seriously. The relationship between information and space-time may be far deeper than the older picture imagined. Distance in ordinary life feels absolute. Here is here, there is there, but quantum theory suggests that physical connection is not exhausted by distance. Two systems can be far apart in space and still share one quantum description, not in a way that allows messages to travel instantly, but in a way that shows the classical concept of separateness is incomplete. This is why entanglement feels like distance has stopped behaving normally. Space still matters, signals still obey limits, but information does not always sit neatly inside isolated objects. The connection itself can be part of the state. This is not an easy idea to live with. It asks us to abandon one of the deepest assumptions of ordinary thought, that reality is made from independent pieces first, and relationships second. Quantum physics may be telling us that relationships can be just as fundamental as the pieces they connect. A particle is not always fully described alone. A system is not always reducible to its components. The whole can be more than the sum of its parts, not poetically, but physically. Entanglement is the mathematics of that fact, and perhaps that is why it remains one of the most unsettling discoveries in science. It does not destroy reality. It does not make the universe unreal. It does something more difficult. It shows that reality is ordered in a way our ordinary categories cannot fully contain. The world beneath matter is not made only of objects, it is also made of states, correlations, shared information, connections that cannot be replaced by classical stories about hidden instructions. The universe is not a collection of isolated facts scattered through empty space. At the quantum level, some facts belong to relationships. Some information is not located in one particle or another, but in the structure connecting both. Entanglement does not let us speak faster than light, but it does let nature be connected more deeply than classical physics allowed. And in that quiet difference, quantum physics reveals one of its strangest truths. Distance may separate objects, but it does not always separate the information that defines them. Measurement is the point where quantum physics becomes most difficult to translate into ordinary language. Before measurement, a quantum system can be described as a structure of possibilities, not loose possibilities, not guesses in the casual sense. A precise physical state governed by mathematical rules, containing the possible outcomes that could appear if the system interacts with the world in a particular way. After measurement, one outcome is recorded. A detector clicks, a photon is absorbed, an atom changes energy, a mark appears in an instrument, a number becomes part of the data. The strange question is, what happened between those two descriptions? Before the measurement, the system was not always behaving like a tiny classical object, with one fully definite answer hidden inside it. It may have been in a superposition, a quantum state containing multiple possible outcomes. After the measurement, the world contains one result, one record, one fact that can be copied, stored, compared, and remembered. This transition is known as the measurement problem, and it remains one of the deepest unresolved questions in the foundations of physics. In everyday life, measurement feels simple. If we measure the length of a table, we assume the table already had that length. If we check whether a lamp is on or off, we assume the lamp had a definite state before we looked. If we open a box and find a coin showing heads, we assume it landed that way earlier. Measurement in the classical world is usually discovery. The property exists first. The observer finds it later. Quantum mechanics complicates that picture. A quantum system can be prepared in a state where the theory gives probabilities for different outcomes, but does not always say that one of those outcomes was already real. In the ordinary sense before measurement, the state contains structured possibility. The measurement produces a definite record, and between possibility and record lies the mystery. Does measurement reveal a property that already existed, or does it help create the outcome? That question has no single agreed-upon answer. Quantum mechanics tells us how to calculate the probabilities. It tells us how the state evolves when isolated. It tells us what results to expect over many repeated experiments. But what the quantum state means, and what exactly happens when one outcome becomes definite, remains a matter of interpretation. This is where caution matters. Measurement does not mean that human consciousness magically creates reality. That idea is popular but misleading. In physics, measurement is not necessarily a person looking at something. It is a physical interaction that produces a stable record. A particle hitting a detector can be a measurement. A photon being absorbed by an atom can be a measurement. A quantum system becoming entangled with its environment can act like a measurement. A mark left in matter, radiation, or an instrument can become a record, even if no human being sees it at the moment. The universe was producing records long before there were observers with minds. Stars emitted light. Atoms interacted. Particles scattered. Radiation left traces. Physical systems became correlated with other physical systems. Reality did not wait for consciousness to begin behaving physically. But that does not remove the mystery. It only makes the mystery more precise. Measurement is a physical process, but it is not just any physical process. It is the kind of interaction that turns fragile quantum information into a definite, accessible result. Before measurement, the system may contain possibilities that can interfere. After measurement, the interference is no longer available in the same way. The outcome has become part of the classical world. A stable record exists, and once a record exists, it changes what can be known. This is why measurement is so central to quantum physics. It is the bridge between the hidden structure of the quantum state and the world of observed facts. The quantum state tells us what may happen. Measurement tells us what did happen, yet the bridge is not fully understood. One reason is that quantum theory describes isolated systems differently from measured systems. When a system evolves without being measured, its state changes smoothly according to quantum rules. But when a measurement occurs, the description seems to shift. The range of possible outcomes gives way to one recorded result. That shift is easy to use in calculations. It is much harder to explain as a picture of reality. Some interpretations say the quantum state represents a real physical wave, and measurement causes it to collapse into one outcome. Others say the state represents information, and measurement updates what can be known. Some suggest that all possible outcomes occur in a larger branching structure, with observers finding themselves in one branch. Others look for deeper physical mechanisms that make outcomes definite. Each interpretation tries to explain the same experimental facts. None has completely ended the debate, but all serious interpretations must respect what experiments show. Quantum systems can display interference before measurement and definite outcomes after measurement. Any explanation must account for both. The double nature of measurement can be felt in a simple idea. Before interaction, a quantum system may behave as though multiple possibilities matter, not as a vague metaphor, but in measurable interference patterns. After interaction with a measuring device, one result appears. The detector does not record a cloud of possibilities. It records a click, a position, an energy, a spin value. The world of experience is made of clicks, but the world beneath those clicks is described by quantum states. This is the tension. Quantum possibilities are not ordinary ignorances. They can interfere, combine, and cancel. If a particle were merely hiding a classical answer all along, many quantum experiments would not produce the patterns we observe. The possibilities seem physically active before measurement. They shape what can happen, and yet, when measured, only one result is found. Not a blur, not a list. One. This is the moment reality becomes definite to an observer, but definite does not mean absolute in every philosophical sense. It means a stable record exists within the physical world. Something has interacted strongly enough with the system to preserve a result. That result can be read, copied, and included in later events. It has become part of history. This is where the environment plays an important role. Quantum systems are fragile when isolated. They can remain in delicate superpositions, but large objects constantly interact with their surroundings. Air molecules collide with them. Light reflects from them. Heat moves through them. Every interaction carries away information. The environment becomes a vast network of records. This process, called decoherence, helps explain why the everyday world looks definite. It shows how quantum possibilities become effectively hidden when a system becomes entangled with countless environmental degrees of freedom. The delicate relationships that allowed interference spread outward into the environment, becoming practically impossible to reconstruct. What remains for observers is a classical-looking outcome. Decoherence does not answer every philosophical question about why one outcome is experienced rather than another, but it explains why the quantum world so often gives way to the stable world we know. A table does not appear to hover in visible superposition because it is never truly isolated. Its quantum information is constantly being shared with the surrounding universe. The world is always measuring it, not consciously, but physically. In this sense, measurement is not rare, it is everywhere. Every interaction can create correlations. Every correlation can carry information. Every stable record can turn a possible event into part of the world's factual structure. The universe is continuously transforming quantum possibilities into classical traces. But in laboratories, scientists can slow this process down. They isolate atoms, photons, ions, superconducting circuits, and other quantum systems. They protect them from the environment long enough to preserve superposition, entanglement, and interference. Then they choose how to measure them. They ask a physical question with a physical apparatus, and the system responds with one outcome. The choice of measurement matters. Different experimental setups can reveal different properties. A quantum system may not carry definite answers to every possible question at once. What becomes definite depends on the interaction used to measure it. The apparatus defines the kind of question being asked. The quantum state defines the possible answers. The measurement produces the result. This is not subjectivity in the ordinary sense. It is not personal opinion. It is physical context. The result depends on how the quantum system is physically coupled to the measuring device. Nature answers the question that the experiment actually asks, not every question at once. That is another reason quantum measurement feels so strange. It challenges the idea that properties simply sit inside objects, fully formed, independent of all interactions. At the quantum level, some properties may become definite only in the context of measurement. Reality is not less real because of this, but it is less classical. It is relational, interactive, structured by what can be measured and how. This mystery reaches beyond the laboratory. It touches how the classical universe emerges from quantum laws. The early universe was once governed by quantum fields. Tiny fluctuations may have been stretched to cosmic scales, eventually seeding galaxies. Every atom in every star follows quantum rules. Every photon reaching Earth carries a quantum history. The definite world we live in may be the accumulated result of countless interactions, turning possibilities into records. We live inside a universe of outcomes. But beneath those outcomes is a deeper layer of probability, amplitude, entanglement, and measurement. This is why the measurement problem is not just a technical puzzle. It is a question about how reality presents itself. How does the world of possible outcomes become the world of actual events? Is measurement merely the revealing of hidden facts? Or is it the physical act by which certain facts become real within a specific context? Physics does not yet give one final answer, but it gives us something powerful: the ability to predict the patterns with extraordinary precision, even while the meaning remains debated. That combination is unusual. Quantum mechanics is both deeply practical and deeply mysterious. It can build technologies, guide experiments, and explain matter, while still leaving open the philosophical question of what measurement really is. Perhaps that is why measurement feels like the threshold of reality. Before it, the quantum state contains what can happen. After it, the world contains what did happen. Before it, possibilities can interfere. After it, a record remains. Before it, information is delicate, structured, and not fully classical. After it, information becomes a fact that can enter memory, data, and history. The universe does not need consciousness to make this transition, but it does need interaction. It needs a physical process that links the system to something larger, something capable of preserving a result. Measurement is not a human gaze. It is the creation of a record, and a record is one of the ways reality becomes stable. The mystery is that the record always contains one outcome, while the quantum state that led to it may have contained many possibilities. That gap remains one of the most profound openings in science. Does measurement reveal what was already there? Does it help create what becomes there? Or are both questions shaped by classical language trying to describe something deeper? For now, quantum physics leaves us with a careful, unsettling truth. Reality is not simply waiting as a finished list of properties. At its deepest accessible level, it contains possibilities governed by precise rules. Through measurement, those possibilities become recorded outcomes. The world becomes definite, not by magic, but through physical interaction. And every detector click, every absorbed photon, every mark left in matter is a small moment in which the quiet structure of possibility becomes part of the history of the universe. The deeper physics goes, the less matter looks like a collection of tiny objects. At first, the world seems built from things: stones, oceans, bodies, planets, stars. Break those things apart, and we find molecules. Break molecules apart, and we find atoms. Break atoms apart, and we find electrons around nuclei. Break nuclei apart, and we find protons and neutrons. Break those apart, and we find quarks and gluons. It is tempting to imagine that this process simply continues towards smaller and smaller pieces. A universe made from particles, a cosmic construction set, tiny objects placed inside space. But modern physics suggests a deeper picture. Particles may not be the most fundamental things. Fields may be. A quantum field is not a field in the ordinary sense of a farm or a surface. It is a physical entity spread throughout space, capable of taking on different states, carrying energy, interacting with other fields, and producing what we recognize as particles. Every known particle is associated with a field. The electron belongs to the electron field. The photon belongs to the electromagnetic field. Quarks belong to quark fields. Gluons belong to gluon fields. The Higgs boson belongs to the Higgs field. In this view, particles are not tiny solid beads moving through an empty background. They are localized excitations of fields. A particle is what happens when a field is disturbed in a particular quantized way. It is a small packet of field activity, a measurable event, a ripple with the properties we call mass, charge, spin, and energy. The particle is real, but it is not real as a little ball. It is real as an excitation of something deeper. This changes the entire emotional shape of matter. The universe is not empty space filled with particles. The universe is filled with fields. Particles are how those fields reveal themselves. This idea is difficult because our senses evolved in a world of objects. We touch surfaces, we hold tools, we see boundaries, we move through rooms and landscapes where one thing seems separate from another. A table is here, a wall is there, a hand reaches across distance. The world appears to be made from solid parts arranged inside space. But at the quantum level, solidity is an emergent experience. The table is stable because quantum fields and forces organize matter into atoms and molecules. Your hand does not pass through it because electrons, electromagnetic interactions, and quantum rules resist the overlap of matter in familiar ways. What feels like contact is the large-scale result of invisible field interactions. The solidity is real, but the foundation beneath it is not solid in the everyday sense. It is field-like. Even what we call empty space is not simply nothing. This may be one of the most unsettling ideas in modern physics. Empty space is not a blank void waiting for objects to enter. It is the lowest energy condition of quantum fields. It contains the possibility of excitations. It contains fluctuations. It contains structure defined by the fields that exist everywhere, even when no particles are present. Nothing, in quantum physics, is not as empty as common sense imagines. A perfect vacuum is not a region where reality has been removed. It is a region where fields are in their ground states. Those fields can still fluctuate. They can still influence physical effects. They can still define what kinds of particles are possible if enough energy is supplied. Space is not just a stage. It is part of the machinery. And the machinery is invisible. The electromagnetic field, for example, is present everywhere. When it is excited in the right way, we call that excitation a photon. Light is not made of tiny glowing pellets in the classical sense. It is the quantum excitation of a field that fills space. When a photon is emitted by an atom, travels through space, and is absorbed somewhere else, the event can be described as a quantum field exchanging energy and information. The electron field is also everywhere. An electron detected in a laboratory, inside an atom, or near a distant star, is an excitation of that same universal field. This helps explain why all electrons are identical. They are not separate little objects manufactured in different cosmic workshops. They are excitations of one underlying field, obeying the same rules everywhere in the universe. That universality is profound. It means the matter in your body and the matter in a galaxy billions of light years away are not merely similar by coincidence. They arise from the same underlying quantum fields. The same fields that shaped the early universe are still active now. The same invisible machinery that governs a particle detector also governs stars, nebulae, planets, and living cells. The world is local in experience, but universal in foundation. Quantum fields also change the meaning of creation and destruction. In ordinary life, if an object is destroyed, it seems to disappear as that object. A glass shatters, a candle burns, a machine breaks. But in quantum field theory, particles can be created and annihilated as field excitations. Energy can become particles. Particles can transform into other particles. What remains deeper than the individual particle is the field and its laws. An electron may appear in an interaction. A photon may be emitted or absorbed. A particle may decay. But the field remains. The field is the underlying possibility from which particles can arise. This is why high-energy particle collisions are so revealing. When particles smash together with enough energy, the collision does not simply break them open like mechanical objects. Instead, energy is concentrated into a tiny region, and quantum fields respond. New excitations can appear. Particles that were not present before can be produced. The event is less like cracking a stone to see smaller stones inside, and more like striking the invisible fields hard enough for their possible excitations to become real. Matter at that level is dynamic. It is not a static inventory. It is a performance of fields under rules. Even mass itself becomes more subtle. Some particles acquire mass through interaction with the Higgs field, which has a non-zero value throughout space. This does not mean the Higgs field is a thick substance, slowing particles down in a simple mechanical way. It means the properties of particles are shaped by their relationship with a field that permeates the universe. Again, the lesson repeats. What a particle is depends on fields. What it can do depends on fields. What appears as matter is deeply tied to the state of fields. This is the invisible machinery beneath matter. Not machinery made of gears, not machinery built from parts smaller than particles, but machinery in the sense of lawful structure, fields, states, symmetries, interactions, excitations, and constraints. A deep order that does not look like the world it produces, but gives rise to it. The word field may sound calm, but quantum fields are not passive. They interact. They exchange energy. They allow forces to occur. They determine which particles can exist, how particles behave, how they decay, how they scatter, and how they combine into the structures of matter. The strong force binds quarks inside protons and neutrons. The electromagnetic field allows atoms and chemistry. The weak interaction allows certain particles to transform. The Higgs field helps shape particle masses. These fields are not decorations added to reality. They are realities working language at the deepest experimentally tested level, and this leads to a more radical possibility. Perhaps reality is not made of objects placed inside space. Perhaps it is made of fields whose states define what particles can appear, how they move, and how they interact. Objects may be the surface story. Fields may be the deeper grammar. A particle is like a word spoken by a field. A detector event is like a moment when that word becomes audible. A force is like a rule describing how fields speak to one another. The analogy is imperfect, but it captures something important. The basic ingredients of reality may not be isolated things, but continuous structures capable of producing discrete events. That is one of the great surprises of quantum field theory. It combines continuity and discreteness. Fields extend across space, yet their excitations appear in quantized units. Light spreads like a wave, yet is detected as photons. Matter behaves as localized particles, yet arises from fields. The universe does not choose between wave and particle in the way our classical categories demand. It uses a deeper structure in which both are partial views. This also explains why ordinary language struggles. When we say particle, we imagine a tiny object. When we say field, we imagine something smooth and spread out. Quantum fields are neither purely one nor the other in everyday terms. They are physical systems whose excitations can behave as particles, whose states can spread as waves, and whose interactions produce the matter and radiation we observe. The deeper we go, the less reality resembles a collection of little things, and yet the world remains stable. Atoms still form, molecules still hold together, planets still orbit stars, bodies still exist. The classical world emerges from the quantum field world, through vast numbers of interactions, through decoherence, through stable patterns that survive at large scales. The field picture does not erase the familiar world. It explains why the familiar world can exist. This is where the scientific mystery becomes almost philosophical. If matter is not fundamentally a collection of solid objects, then what are we? Our bodies are patterns in fields. Our thoughts depend on quantum-built matter arranged into living systems. The atoms in the brain are not little hard spheres, but stable structures emerging from quantum rules. The solidity of experience is real, but it is built from something far less solid than experience suggests. We are field excitations arranged into chemistry, chemistry arranged into biology, biology arranged into awareness, and awareness is now trying to understand the fields that made it possible. There is a quiet circularity in that. Quantum fields are not distant abstractions. They are beneath every breath, every heartbeat, every photon entering the eye, every signal moving through a nerve. They are also beneath starlight, nuclear fusion, cosmic radiation, and the early universe. The same framework that explains particles in a laboratory also reaches toward cosmology, black holes, and the question of why there is something rather than nothing. Even the vacuum has become part of that question. If empty space contains fields, and fields can fluctuate, then emptiness is not the opposite of existence. It is a state of existence. The absence of particles is not the absence of physical structure. The vacuum can influence forces, particle masses, and cosmic behavior. It may even connect to some of the deepest puzzles in physics, including dark energy and the expansion of the universe. So when quantum physics reveals something deeply strange, this is one of its most important revelations. The world is not built the way our senses first told us. Matter is not made from little solid things in the way we imagine. It is built from quantum states and fields. Particles are local events in a deeper field structure. Empty space is filled with invisible possibility, and reality, at its foundation, may be less like objects moving through a void, and more like fields changing state, producing the particles, forces, and stable forms that eventually become the universe we know. Quantum strangeness matters because it does not stay locked inside philosophy. It is easy to treat quantum physics as a distant intellectual puzzle, a strange set of ideas about particles, waves, uncertainty, and measurement. It seems to belong to laboratories, equations, and arguments about what reality means. But quantum physics is not only a mystery at the edge of thought, it is also one of the most practical theories ever discovered. The modern world is built on it, not symbolically, literally. Every smartphone, computer, camera sensor, laser scanner, medical imaging system, and precision clock depends on rules that would make no sense in classical physics alone. The same strange behavior that challenges our intuition also makes our technology possible. Quantum mechanics may feel abstract, but it is operating silently inside the devices we use every day. Semiconductors are a clear example. The digital world depends on the controlled movement of electrons through materials, but electrons in a semiconductor do not behave like tiny classical balls flowing through wires. Their behavior depends on quantum energy bands, allowed states, forbidden gaps, and the way electrons respond to the structure of atoms inside the material. Without quantum physics, modern electronics would not exist in the form we know. A computer chip is not just a piece of engineered metal and silicon. It is quantum physics organized into logic. Every calculation, every image, every signal, every stored message depends on matter behaving according to rules discovered at the microscopic level. The devices feel ordinary because they are familiar, but beneath their surfaces is a world of quantum states made useful through engineering. Lasers are another example. A laser does not work because light is simply bright. It works because atoms, atoms, and photons obey quantum rules. Electrons occupy specific energy states. They can absorb energy, jump to higher states, and then release photons in controlled ways. Under the right conditions, many photons emerge with the same frequency and phase relationship, producing a beam of remarkable coherence. That coherence is not a classical accident. It is quantum order made visible. Lasers cut materials, scan barcodes, carry information through fiber optic cables, guide measurements, perform surgery, and help scientists probe the structure of matter. One of the strangest features of quantum physics, the discrete energy levels of atoms, became one of the most useful technologies humans have ever built. Then there are MRI machines. Inside hospitals, magnetic resonance uses quantum properties of atomic nuclei to create detailed images of the body. The technique depends on how nuclear spins respond to magnetic fields and radio waves. The result is a medical technology capable of revealing soft tissues, organs, and structures inside the human body without cutting it open. A patient entering an MRI scanner is not thinking about quantum mechanics. But quantum mechanics is part of why the image exists. It is part of how invisible structure becomes visible information. Atomic clocks also depend on quantum physics. They measure time using the extremely stable transitions of atoms. These transitions are not mechanical ticks in the old sense. They are quantum events governed by precise energy differences. Because these transitions are so reliable, atomic clocks can measure time with extraordinary accuracy. And that accuracy matters. Navigation systems, telecommunications, scientific measurements, and global positioning all depend on precise timing. The ability to know where something is on Earth can depend on quantum transitions inside atoms. The abstract becomes practical. The microscopic becomes planetary. Quantum sensors push this even further. By exploiting delicate quantum effects, scientists can build instruments capable of measuring tiny changes in gravity, magnetic fields, acceleration, and time. These sensors may help map underground structures, detect subtle signals, improve navigation, and test fundamental physics. The same fragility that makes quantum states difficult to preserve can also make them exquisitely sensitive to the world around them. And then there are quantum computers. They are still emerging, still difficult, still far from replacing ordinary computers for everyday tasks. But their promise comes from one of quantum physics' strangest features: the ability to process information using superposition, interference, and entanglement. A quantum computer is not just a faster classical machine. It is a different kind of machine, one that uses the structure of quantum possibility to solve certain problems in new ways. Whether quantum computers become broadly transformative remains an open question. But their existence already proves something important. Quantum strangeness is not merely philosophical. It can be engineered. It can be cooled, isolated, controlled, measured, and turned into technology. This is why the strange discovery matters. Quantum physics is not a decorative mystery added to reality after the practical work is done. It is the foundation beneath much of the practical world. The parts that seem most unsettling, quantized energy, wave-like matter, probabilistic outcomes, entanglement, and measurement, are not optional curiosities. They are part of the machinery that makes matter behave as it does. But the importance does not stop with technology. The same quantum principles that shape electronics and lasers may also connect to the deepest mysteries in cosmology. The smallest rules may explain the largest mysteries. That is the emotional bridge. Quantum physics is not only the science of tiny things. It may be the language needed to understand black holes, dark matter, the early universe, and the structure of space-time itself. The microscopic and the cosmic are not separate worlds. They are connected by laws that operate across scale. Black holes bring this connection into sharp focus. A black hole is created by gravity, but its deepest puzzles involve quantum information. If something falls into a black hole, what happens to the information it carried? Is it destroyed, hidden, scrambled, or somehow returned through radiation? This question is not just about distant objects in space. It is about whether quantum mechanics and gravity can both be true in their current forms. Black holes force physics to confront the limits of its two greatest frameworks. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes the behavior of matter, energy, and information at the smallest scales. Both work brilliantly, but together at the edge of a black hole, they create questions we have not fully answered. Dark matter may also be tied to quantum physics. Galaxies rotate as if they contain far more mass than what we can see. Clusters of galaxies bend light in ways that visible matter cannot explain. The cosmic web itself seems shaped by an invisible gravitational presence. If dark matter is made of particles, those particles are part of quantum physics. They may belong to a hidden sector, interacting weakly with ordinary matter, leaving only faint traces in detectors or cosmic structure. A discovery at the quantum level could become a clue to the invisible mass holding galaxies together. A tiny particle could explain a cosmic architecture. The early universe brings the connection even deeper. In its first moments, the universe was not filled with planets, stars, or galaxies. It was filled with fields, radiation, particles, and extreme conditions where quantum effects may have shaped everything that followed. Tiny quantum fluctuations may have been stretched into the seeds of galaxies. The large-scale structure of the universe may have begun as microscopic variations in quantum fields. What became galaxies may have started as quantum uncertainty. That idea is both technical and profound. The cosmic web, the enormous structure of galaxies and clusters across the universe, may trace back to tiny quantum differences in the earliest moments of cosmic history. The smallest possible disturbances may have grown under gravity into the largest structures we observe. This is why quantum physics changes the emotional scale of science. It shows that the universe is connected from bottom to top. The rules governing particles are not isolated from the rules governing stars. The behavior of fields is not separate from the formation of galaxies. The meaning of information in quantum theory may not be separate from black holes and space-time. The strange microscopic rules may be the hidden script behind the cosmic story. Quantum gravity is the name given to one of the greatest unfinished tasks in physics. Finding a way to describe gravity using quantum principles, or discovering a deeper theory from which both gravity and quantum mechanics emerge. This is not only a mathematical challenge, it is a question about what space-time really is. Is space-time smooth all the way down, or does it have quantum structure? Could geometry emerge from entanglement? Could gravity be connected to information? Could the distance between things be related, at the deepest level, to patterns of quantum correlation? These are not settled answers. They are frontier questions, but they show why quantum strangeness matters. It is not merely about particles behaving oddly in laboratories. It may be pointing toward a deeper architecture beneath reality itself. The same theory that explains semiconductors also raises questions about black holes. The same principles that make lasers possible may be connected to the behavior of fields in the early universe. The same idea of quantum information that helps build quantum computers may help physicists understand whether space-time emerges from something deeper. Technology is the proof that quantum physics works. Cosmology is the reminder that we still do not fully know what it means. That combination is rare. A theory can be useful without being philosophically complete. Quantum mechanics is useful beyond anything its founders could have imagined, and yet its deepest interpretation remains open. It builds devices, heals bodies, guides navigation, measures time, and predicts experiments with extraordinary precision. But it also asks what reality is before measurement. what information means, why probability and abilities appear fundamental, how matter emerges from fields, whether entanglement is connected to space-time, and whether the universe is built from objects or from relationships beneath objects. This is why quantum physics remains so powerful as a scientific story. It is not just strange for the sake of being strange. Its strangeness has consequences. It gives us technology, but it also gives us humility. It tells us that the world our senses present is not the final layer. Beneath ordinary matter is a set of rules that are subtle, mathematical, and deeply non-classical. The smallest rules may explain the largest mysteries. A quantum transition can power a clock. A quantum field can shape matter. A quantum fluctuation can seed a galaxy. A quantum information puzzle can challenge our understanding of black holes. A quantum measurement can force us to ask what it means for a fact to become real. That is why this strange discovery matters. Because every time quantum physics reveals something deeper, it changes both what we can build and what we think we are living inside. The universe is not only vast above us, it is also deep beneath us. And the path to understanding the largest structures in existence may begin with the smallest rules reality allows. There is a quiet honesty at the frontier of physics. After more than a century of experiments, calculations, discoveries, and technologies built from quantum theories, scientists still do not fully agree on what the theory is telling us about reality. They agree on how to use it. They agree on its predictions. They agree that it works with extraordinary precision. But when the question shifts from what does quantum mechanics predict to what does quantum mechanics mean, the ground becomes less settled. That uncertainty is not a failure. It is where science continues. Quantum physics is not broken. It is not a guess waiting to collapse. It is one of the strongest frameworks ever created for describing the natural world. It explains atoms, molecules, light, radiation, materials, chemistry, semiconductors, lasers, magnetic resonance, and the behavior of particles in high-energy experiments. It has been tested again and again, and nature has answered with remarkable consistency. The mystery is not whether quantum physics works. The mystery is why it works in such a strange way. Physicists still debate what the quantum state really means. Is it a real physical thing, something that exists in the world as part of reality itself? Or is it a tool for organizing knowledge, a mathematical description of what an observer can expect to measure? Does it describe nature directly, or does it describe our relationship to nature? This question matters because the quantum state is central to the whole theory. It tells us the possible outcomes of measurements. It tells us how probabilities evolve. It contains the structure that produces interference, entanglement, and quantum behavior. Yet its interpretation remains open. Some physicists think the quantum state is ontic, meaning it reflects something real about the world. Others see it more as epistemic, meaning it represents information or knowledge about possible outcomes. Still others argue that the usual categories are too limited, that the quantum state points toward a deeper framework we have not yet found. The debate continues because quantum mechanics gives clear predictions without giving one simple picture. Measurement remains another unresolved question. Before measurement, a quantum system can exist in a structured range of possibilities. After measurement, one outcome is recorded. The detector clicks. A value appears. The world contains a fact. But what exactly happens when possibility becomes a recorded result? Does the measurement reveal a property that already existed? Does it help create the outcome? Does the quantum state collapse in a real physical sense? Or does the appearance of collapse come from the way systems become entangled with their environments? There are many interpretations. Some suggest that all outcomes happen in a larger branching structure. Some treat collapse as a fundamental physical process. Some focus on information, observation, and consistency between records. Some search for deeper hidden variables, though experiments severely restrict what those hidden variables could be. No interpretation has become the final word, and yet the experiments still work. This is one of the strange features of quantum physics. It is possible to calculate with great confidence, while still debating the meaning of the calculation. That may feel uncomfortable, but it is not unusual in deep science. Sometimes a theory becomes mathematically powerful before human intuition catches up. Sometimes nature gives us rules long before it gives us a picture we can fully understand. Gravity presents another unfinished bridge. Quantum mechanics describes the microscopic world with astonishing success. General relativity describes gravity, space-time, and cosmic structure with equal brilliance. But the two theories do not fit together completely. In ordinary situations, this is not a practical problem. Quantum effects are usually tiny on cosmic scales, and gravity is usually weak on particle scales. But there are places where both must matter. Inside black holes, near the Big Bang, at extreme densities, at scales where space-time itself may no longer behave smoothly. There, our current theories strain. A complete theory of quantum gravity remains one of the deepest goals in physics. Scientists do not yet know exactly how gravity should be described in quantum terms, or whether gravity itself is fundamental in the same way as the other forces. Some approaches try to quantize spacetime directly. Others suggest spacetime may emerge from deeper quantum structures. Still others look for new principles connecting information, geometry, and entanglement. This uncertainty does not mean relativity is wrong or quantum mechanics is useless. It means each theory may be part of a larger structure that has happened before. Newton's laws still work beautifully within their domain, even though relativity revealed a deeper picture of space, time, and gravity. Classical physics still work everyday life, even though quantum mechanics revealed a deeper picture of matter. A future theory may not destroy quantum mechanics. It may explain why quantum mechanics works, and where it fits inside something wider. Then there is spacetime itself. For most of human history, space seemed like the place where things happen, and time seemed like the order in which they happen. Relativity changed that picture by showing that space and time are linked, flexible, and shaped by matter and energy. But quantum physics may be asking an even deeper question. Is spacetime fundamental, or does it emerge from something beneath it? Some modern ideas suggest that entanglement and quantum information may be related to the structure of spacetime. Perhaps geometry is not the starting point. Perhaps the distance between regions, the shape of space, and even aspects of gravity arise from deeper patterns of quantum correlation. This is not settled science, it is frontier work. But it is serious enough to reshape how physicists think about reality. Black holes, entropy, holographic ideas, and quantum information have all pointed toward a surprising possibility. Space-time may not simply contain information. It may be built, in part, from informational structure. If that is true, then the universe is stranger than the old picture of objects moving through a pre-existing stage. The stage itself may be part of the performance. Still, humility is essential. Not every elegant idea is true. Not every mathematical possibility describes nature. Physics advances by testing, refining, rejecting, and rebuilding. Some ideas will fail. Some will survive. Some will become stepping stones toward theories no one has yet imagined. That is not weakness. That is the method. Uncertainty in science does not mean ignorance without direction. It means the questions have become sharp enough to guide the search. When physicists say they do not know what the quantum state really means, they are not admitting defeat. They are naming a boundary. When they debate measurement, they are not denying quantum mechanics. They are trying to understand why the theory gives the world we experience. When they struggle to connect quantum mechanics with gravity, they are not saying physics has collapsed. They are standing at the edge where a deeper theory may be required. This is how science remains alive. A finished science would ask no more questions. A living science knows where its answers end. Quantum physics has answered more about the microscopic world than any earlier theory could have dreamed. It has revealed the structure of atoms, the behavior of light, the stability of matter, and the hidden rules behind modern technology. It has given us tools powerful enough to manipulate single particles, entangle systems, build quantum devices, and measure nature with extraordinary sensitivity. But it has also left us with deeper questions. What is a quantum state? What is measurement? Why does one outcome appear? How does the classical world emerge? How does quantum theory connect with gravity? Is space-time fundamental? Is information part of the foundation of reality? These questions are not signs that quantum physics has failed. They are signs that quantum physics has succeeded deeply enough to reveal the next layer of mystery. That is often how progress feels at the frontier. The better the map becomes, the more clearly we see the blank spaces. The blank spaces are not evidence that the map is useless. They are invitations to continue. The universe is not obligated to be simple. It is not obligated to match human intuition. It is not obligated to answer every question in the language that feels comfortable to us. But it does answer experiment. It leaves patterns. It allows measurement. It gives enough structure for minds to build theories, and enough mystery for those theories to keep growing. That may be the most reassuring truth. Quantum physics is powerful because it is tested. It is incomplete because reality is deep. The uncertainty at its edge is not a crack that makes the whole structure collapse. It is a doorway. Beyond that doorway may be quantum gravity, a deeper theory of measurement, a new understanding of space-time, a clearer view of information, or an idea no one has yet learned how to ask. For now, science continues in the space between confidence and humility. It trusts what has been tested, questions what remains unclear, and keeps listening where reality still speaks in signals too subtle for ordinary senses. Quantum physics is not broken. It is powerful, precise, and unfinished at the frontier. And that unfinished edge may be exactly where the next great understanding begins. Reality is not obligated to be intuitive. That may be the quietest and most important lesson quantum physics has given us. For most of human history, the world appeared to be made from solid things moving through space. Stones, rivers, bodies, planets, stars. Objects seem to have clear locations, clear properties, and clear histories. A thing was here or there. A cause produced an effect. A measurement revealed what was already true. This picture was not foolish. It worked. It still works across the scale of ordinary life. It lets us build houses, navigate oceans, launch spacecraft, and predict the motion of planets. It is the map our senses gave us, refined by centuries of science. And for the world of human experience, it remains non powerful. But a map is not the territory. At the deepest levels we can test, reality does not behave like the simple map. Matter is not made of tiny solid balls in the way our imagination first suggests. Particles behave like localized events, but they arise from quantum fields. They can appear as points when measured, yet before measurement, their behavior may be spread across structured possibilities. Empty space is not simply empty. It contains fields, fluctuations, and the potential for excitations. What looks like nothing may still carry physical structure. What looks like a particle may be a ripple in something deeper. What looks like certainty may emerge from a layer where probability is not ignorance, but part of the law. This does not make the universe unreal. It makes it deeper. Quantum physics has not shown that reality is an illusion. It has shown that reality is not limited to the categories that feel natural to us. Solidness, location, separateness, and certainty are not false, but they may be emergent. They may be the large-scale language of a world built from something more subtle beneath. A table is real, a star is real, a human body is real, but their reality is not the simple reality of hard pieces stacked together. They are stable patterns produced by quantum fields, forces, atoms, interactions, and information. Their solidity is what quantum laws become when countless particles and fields organizes into structures large enough to behave classically. The familiar world is not denied by quantum physics. It is explained by something stranger. That is why the theory can feel unsettling. It does not replace reality with fantasy. It replaces a simple reality with a layered one. Beneath the world of objects is a world of states. Beneath the world of certainty is a world of probabilities. Beneath the world of distance is a world where entanglement reveals correlations stronger than classical physics allows. Entanglement is one of the clearest signs that our map is incomplete. In the ordinary view, information belongs to objects. One particle has its properties, another particle has its own. Space separates them, but in quantum mechanics, information can belong to the relationship between systems. The full state may not be reducible to the parts alone. The connection becomes part of the description. This does not let us send messages faster than light. It does not break every rule. But it does show that separateness, one of the deepest assumptions of common sense, is not always fundamental. The universe is not always a collection of independent things with relationships added later. Sometimes the relationship is part of what the thing is. Measurement deepens the mystery. Before measurement, a quantum system can contain structured possibilities. After measurement, one outcome is recorded. A detector clicks. A fact enters the world. The question of what exactly happens in that transition remains one of the most difficult in physics. Does measurement reveal a property that was already there? Or does the interaction help produce the outcome? The answer is still debated, but the process is real. Measurement is not human consciousness magically creating the universe. It is physical interaction producing a stable record. Yet, even with that careful definition, the mystery remains. Quantum physics describes possibility with extraordinary precision, while our experience is made of definite events. Somewhere between the two, the world we know appears. This is not a failure of science, it is the frontier of science. The power of quantum physics is that it works even when its meaning is difficult. It predicts experiments. It explains atoms. It powers technology. It underlies lasers, semiconductors, atomic clocks, medical imaging, quantum sensors, and the first generations of quantum computers. Its strangeness is not decorative. It is built into the machinery of the modern world, and still, the theory points beyond itself. It raises questions about black holes and information. It challenges us to not unite quantum mechanics with gravity. It suggests that space-time may not be the final stage on which physics happens, but perhaps something that emerges from deeper quantum structure. It hints that the universe may be built not only from matter and energy, but from fields, probabilities, relationships, and information. This is where quantum physics becomes more than a theory of small things. It becomes a question about the whole. The smallest rules may explain the largest mysteries. Quantum fluctuations may have seeded galaxies. Quantum fields fill the vacuum. Quantum information may be tied to black hole horizons. Entanglement may help illuminate the structure of space-time. The behavior of the very small may echo through the architecture of the very large. The universe is connected across scale. A particle in a detector and a galaxy in deep space do not belong to separate realities. They are expressions of the same physical order, seen at different levels. The laws that govern the atom are not isolated from the laws that shaped the early cosmos. The strange does not live only in laboratories. It lives beneath everything, even beneath us. The atoms in the body obey quantum rules. The chemistry of life depends on quantum structure. The light entering the eye is quantum. The matter forming the brain that asks these questions is quantum-built matter. We are not outside the mystery, observing it from a safe distance. We are made from it. That is the humbling part. Human intuition is not the final authority on reality. It is an adaptation to a narrow band of the universe. Medium-sized objects, moderate speeds, warm environments, stable records. It gives us a practical world, not the deepest world. When quantum physics feels strange, it may not be because nature is confused. It may be because we are meeting reality outside the range where intuition was trained. Science extends the senses beyond their native limits. It lets us hear particles too faint to feel, detect fields too subtle to see, and measure correlations too strange for ordinary thought. It teaches us to trust experiment over instinct and mathematics over comfort. The result is not always easy to picture, but it is more faithful to nature. That may be the real meaning of quantum strangeness. Reality is not broken. The map was too simple. The world our senses gave us is real, but partial. It is the surface of a deeper order. Beneath matter are fields. Beneath certainty are probabilities. Beneath separateness are relationships. Beneath measurement are questions about how possibility becomes fact. Beneath space-time itself may be structures of information we have only begun to understand. The universe does not become less real as we look deeper. It becomes less familiar, and perhaps that is what discovery has always done. It removes the world from the center of human expectation. Earth was not the center of the cosmos. The sun was not unique. The galaxy was not the whole universe. Matter was not solid in the way it seemed. Space and time were not fixed in the way we imagined. Quantum physics continues that long correction. It tells us that reality is stranger than the map. Not because the map was useless, but because the territory is richer. The lesson is not despair. It is wonder with discipline. The universe can be understood, but not always in the language of common sense. It can be measured, but not always pictured. It can be lawful, yet deeply surprising. It can produce stable worlds from unstable possibilities, definite histories from quantum probabilities, and conscious observers from fields and matter that began long before life existed. What quantum physics revealed is not that reality is unreal. It is that reality is deeper than the simple map our senses gave us, and somewhere beneath matter, distance, and certainty, the universe may still be hiding its most important rules. Good night, and see you in the next video.